So we're going to look at a couple of type 1 projectile motion problems now. So here's our first problem. It's called how fast do you need to run off a cliff? So divers in Acapulco dive from a cliff that is 61 meters high. If the rocks below the cliff extend outward for 23 meters, what's the minimum horizontal speed a diver must have to clear the rocks? So it's good to start one of these problems by drawing a diagram with all the numbers labeled. So I have that over here. You can see the distance that someone would be falling in the vertical direction. We're calling that dy of 61 meters, and it's negative since they'll be falling downward. We also have a displacement in x of 23 meters. And what the problem wants us to do is find that unknown velocity in x. So our first step is we're going to create a horizontal and vertical table with the information that we were given. So I filled in that displacement in x of 23 meters, displacement in y of negative 61 meters, acceleration being equal to g, which is negative 9.8 meters per second squared, and something that's true for all type 1 problems, that initial velocity in the y direction will be 0. Ultimately, we want to be able to find a velocity in x, and if we're going to find a velocity, we'll have to use distance divided by time. We don't have enough information on the horizontal side yet to find time, so we'll have to find time on the vertical side and then copy that number over to the horizontal side of the table. Because the amount of time someone is falling vertically is also the amount of time they have to move horizontally. So starting with the vertical side of the table, we need to find time. So using the variables on the vertical side of the equation, you'll have to look at your equation sheet and pick an appropriate equation. So I selected the fourth one, d equals vit plus 1/2 at squared. And I just rewrote a couple of the variables so that they apply to the y direction. So I have a displacement in y is equal to the initial velocity in y times t plus 1/2 at squared. Since initial velocity in y is 0, that term goes to 0. From there, you can go ahead and plug in the numbers from the vertical side of the table. Take a moment to solve algebraically for time. So you'll have to multiply the 1/2 by negative 9.8 to get negative 4.9. Then you'll divide both sides by negative 4.9 to get 12.45 equals t squared. And you'll finally take a square root to get a time value of 3.53 seconds. From there, you can go back to your horizontal vertical table, fill in that time value on both sides of the table, since we said it would be the same on both the horizontal and the vertical side. Now on the horizontal side of the table, you have a distance and you have a time, so you have enough information to find velocity. So take a moment to solve for velocity using velocity equals distance over time. So you'll take that distance of 23, divide by that time of 3.53 seconds, and you'll get an answer of 6.5 meters per second. So this is pretty fast. You'd have to be running about 14 miles an hour to clear those rocks. So here's our second problem. To give us some context here, there's a group of skiers stuck on top of a mountain with no immediate chance of escape. They've been without food, water, and other supplies for a dangerously long time. The cold, hungry skiers are waiting for desperately needed supplies to be airdropped to them. You're the only person nearby with a pilot's license, and you know it's time for you to step up and be a hero. So do you remember enough high school physics to figure out when to drop the food so it doesn't land too far away from the stranded skiers? So once again, it's a good idea to start by drawing a diagram to keep track of everything you were given in the problem. So over here is a little picture of the scenario. And when I go back over here, here's a really basic diagram. Right, so we have that velocity of the plane. We'll call that our velocity in x. We have that displacement in y of negative 250 meters. And this time we want to solve for that horizontal distance, or that dx. So once again, we'll start by creating a horizontal and vertical table. We'll fill in that dx is the variable we're trying to solve for, and that we were given that velocity in x of 80 meters per second. We'll also fill in that vertical drop distance. We can fill in negative 9.8 meters per second squared for acceleration, and that the initial velocity in y is 0. These two ideas are always true for type 1 problems. Once again, I have enough information on the vertical side to find time. And once I get that time value, I can copy it over to the horizontal side of the table so I can be on my way to finding displacement in x. So go ahead and see if you can take a moment to find the time to fall using the fourth equation on your equation sheet. And you can pause the video and resume when you're ready to see it worked out. So once again, that first term will go to 0 since the initial velocity in y was 0. You can fill in the other variables. So negative 250 equals 1/2 times negative 9.8 t squared. Start by multiplying 1/2 times negative 9.8 to get negative 4.9. You'll divide both sides by negative 4.9 to get 51.02 equals t squared. And then finish by taking a square root to get a time value of 7.14 seconds. Now you can go ahead and update your horizontal and vertical table. So we found that time on the vertical side, which for type 1 problems is equal to the time on the horizontal side. And now that we have two of these three variables on the horizontal side, we have enough information to find displacement. So we'll again use velocity equals distance over time. Remember, that's the only equation we can use on the horizontal side. So I'm going to go ahead and rearrange this equation by multiplying both sides by time. This tells me that displacement is equal to velocity times time. Or using our variables with subscripts, we can say that displacement in x is equal to velocity in x times time. So go ahead and take your velocity in x and multiply by time. So you'll take 80 times 7.14 to get 571.2 meters. So that's the first part of this problem. In part B, they want you to find the magnitude of the velocity of the box as it reaches the ground. So we have to remember that as the box is approaching the ground, it's going to be moving at an angle. At this angle here, shown by the black arrow to be exact. So in order to find that total velocity, we need to figure out what the horizontal and vertical components of that velocity are. So one of the assumptions we have to remember for all projectile motion problems is that there's no acceleration in the horizontal direction, which means that the velocity in x is 80 throughout the entire problem. But because of gravity, the vertical velocity is constantly changing, so I have to calculate that final velocity in the y direction. So I'll use the third equation on the equation sheet to do that. I'll use VF equals VI plus AT. I'll make sure that I'm only plugging in variables for the vertical or y direction. So my initial velocity in y was 0, going back to the horizontal vertical table. Acceleration was negative 9.8, and time was 7.14. After multiplying 9.8 by 7.14, I get a negative velocity of 69.97, negative because the box would be moving downward the moment before it would hit the ground. From there, I'm going to draw a new triangle to show the two components and then the total velocity. So here's my velocity in x of 80 meters per second to the right, my downward velocity in y of about 70 meters per second. And when I find this resultant, that'll tell me the total velocity. So you'll use a squared plus b squared equals c squared to do that. Take a moment to do that. Pause the video. And when you're ready, you can click resume. So you should get 106.3 meters per second as a final answer there for velocity. If we go back up to the original problem, they wanted us to find magnitude of the velocity. So by magnitude, they mean they just want a number with a unit. If it didn't say that, you would have to remember that velocity is both a speed with a direction, but since it says magnitude, we don't have to find that direction. If we did have to find a direction, then going back to this triangle over here, you would have to find this angle theta, but we don't have to do that here. All right, so that's the end of this video. That shows the first two problems in the notes worked out. You can go ahead and try the two problems on the back of your paper. And you can look at either the posted PowerPoint or the sheet that I should have out towards the front of the room to check your work as you're working through those questions. All right, thanks for watching.